And so I'm very excited to introduce our speaker today. So we have Chen Wang from UMass Amherst and soon to be from the University of Toronto to talk to us today. And so a few weeks ago, we had Steve Girvin give a colloquium on bosonic codes with superconducting qubits. And so Chen is going to tell us more about current state of error correcting in that kind of modality. And so with that, Chen, sorry for
Just a tiny bit of electrical shock. All right, yeah, thank you so much, Alicia, for the introduction and for inviting me here to give this talk. So it's a great pleasure to visit JQI, and it's a center of gravity for quantum information science research for a long time. So as I can see, many people are interested in coming into the talk. So it's very nice to see you guys. And today I'm going to tell you about autonomous quantum error correction for bosonic superconducting qubits. So to begin with, let me just take a motivation here. We all know that building a quantum information processing system, especially a universal quantum computer, is very difficult. And the key challenge is that the quantum information doesn't tend to stay for very long. And this is very different from classical information processing. And if you take a look at why is our classical information machine is so robust, it's because it has this self-stabilizing mechanism, which is coming from dissipation. So take a magnetic hard drive, for example. If you have any kind of environmental noise that give you some sort of perturbation to this to your bits, what happens is that environmental dissipation will tend to stabilize it on its own without any kind of a sophisticated logic to do the process. So dissipation is used to extract entropy from the system and stabilize classical information. This is really the underpinning of how we do information processing and the whole domain of digital information processing. So a natural question is, can we use environmental dissipation to stabilize quantum information? That has been a dream for people working in the area, trying to really get quantum computing to work. So to a natural question you may ask if you're not in this area, you may wonder, can a quantum superposition even live under dissipation? Because if you talk to in the sort of the public media and talk about quantum superposition, we think about it as this natural fragile state that lives at two places at once. And it seems like if you have interaction with the environment, it tends to destroy any kind of a superposition. So a trivial but fascinating example, as many of you have learned in quantum mechanical undergrad class, is that some natural states under dissipation environment is actually a quantum superposition. For example, you have a weakly driven damped-driven harmonic oscillator like a pendulum or electrical circuit LC or an optical cavity. If you write down your Hamiltonian, write down a drive, and you put this dissipation operator here, which is the natural operator of single photon loss or single photon loss for a mechanical oscillator, the natural steady state arising just from nature is this coherent state, which is a giant quantum superposition of many photon number states. This is a quantum superposition state. So we already know that if you have drive-driven Hamiltonian, you have the loss that is coming from environmental interaction. It doesn't stop your quantum system to behave quantum mechanically in terms of a stabilizing superposition state. So we can use a Wigner function or in phase space to represent a harmonic oscillator state. This is X and the P or real or imaginary parts of the phase space representation of an oscillator, which I will use throughout this talk. And we often work in the rotating frame so that the oscillator doesn't actually move around in circles on the phase space, but it will be stationary because we typically describe these phenomena in the rotating frame. So of course, the coherent state is a superposition state if you look at it from in the Fock basis. But can dissipation create more interesting states that can actually be used for quantum computing or for other sort of information processing? So we know that the system will relax to a specific quantum state if this quantum state is a stationary state in terms of a eigenstate of a or Hamiltonian, as well as the dissipation operator, which describes the interaction of the system with the environment, acts on the wave function will give you 0. This is known as the dark state condition. So this term of dissipation engineering is coined in the interesting quantum state as the steady state of your quantum system. And this can allow you to prepare, for example, resource states that are interesting for quantum information purposes. So over the years, there have been many various types of demonstration or understanding of engineering specific dissipation operator so that you can stabilize interesting superposition states such as squeeze states, and to stabilize it for example, 2-qubit Bell states, or even stabilizing many body quantum states. So these are interesting ways to stabilize a specific quantum state so that they can function as resources. But in order to do information processing, you have to be able to stabilize many states. For example, if you want to stabilize a qubit, your 0 and 1 would have to be both stable, as well as any kind of a superposition of the quantum state that represents 0 and 1. So a natural extension from stabilizing interesting resource states would be to stabilize a manifold of states. So a natural way to think about this is the bit flip code. So these are proposals for the so-called autonomous bit flip error correction. You can think about as engineered dissipation so that this is analogous to a classical bit. You stabilize your repeating zeros and repeating ones. These will become the attractor in your configuration space. And if you can destabilize any of the intermediate states and erect a sort of energy barrier, as well as making these dissipation to not leak information so that the environment doesn't know which path it has gone through, then you will be able to implement an autonomous code for bit flip correction. And this has been proposed in different physical platforms. These are already looking kind of a sophisticated looking like experiments that you can do. But over the years, people haven't really worked hard to pursue this approach because bit flip is not the most natural form of error that will happen for these kind of physical qubits. And oftentimes you deal with, say, energy decay, which is more natural for various types of qubits. So if you want to move one step further to be able to construct a full quantum error correcting code for both bit flip or phase flip, which will allow you to correct all kinds of errors for single qubits. This is the sort of photonic approach people have come up with. And I don't understand what this diagram really means in terms of components. What I know is that it's complicated enough that nobody has tried to do this, even though this proposal has been a thing for a while. So there's on the other hand, there are also other types of proposals that or experiments people have looked into that will allow you to stabilize a manifold of states that is spanned across a two-dimensional Hilbert space that will allow you to encode the qubit. And this is a form of dissipation that is almost natural to engineer nowadays, at least in superconducting circuits, which is the area I'm going to talk about. So if you engineer this dissipation operator, which is called the two-photon loss, A square, which extracts pairs of photons from a harmonic oscillator mode. And if you put a two-photon drive on it, this is also the squeezing drive, if you're familiar with quantum optics. If you put also a two-photon drive on it, this is the effective dissipation operator that will allow you to allow your quantum oscillator to live at this coherent states of plus alpha or minus alpha, as represented here as a blob on the real positive side as well as the real negative side. Both of these coherent states will be stable will be steady states under this dissipation operator, as well as all superposition states between the plus alpha and minus alpha, which we call the Schrodinger cat state of a harmonic oscillator. This cat state manifold would all be stable under this dissipation. And this allowed people to encode a qubit in this two-dimensional Hilbert space. And this is the so-called phase space stabilization. And it is similar to autonomous error correction in the sense that only these states are stable, but these blobs are not allowed to rotate around on the phase space. So this creates a so-called bias noise cat qubit. But the issue is that it does not correct against the natural dominant error in a typical oscillator system, which is single photon loss. If you have a photon loss in the system, this cat qubit is going to flip in its interference fringes, and therefore it's going to this creates a qubit that is protected against any phase drift, or what we usually call that the bit flip, but it doesn't correct against the phase flip error, which is actually the dominant error in a typical superconducting oscillator or optical cavity. So the strategy, this nonetheless is a very active field of research, because now you can, instead of using a 2D code, you can use a 1D code to build a concatenation on top of this qubit, which is an approach that a few companies, including Amazon AWS, has been pursuing. And this is a very influential work, very beautiful work recently coming out on Nature. They built a chain of 5 of such biased noise stabilize the cat qubit, and they're able to essentially be on the similar footing as the Google Surface Code experiment in terms of comparing different code distances of error correction performance. But I'd like to point out that error correction comes with a very large overhead, because the fact that you need to make 5 cats here in this experiment, you start to incur more decoherence in the system, just because more things can go wrong and more types of error can happen. And if you compare these corrected logical lifetime versus the physical coherence of individual cavities, this experiment, even with its huge accomplishment and the scalability capability in the future, it's currently still slightly below break even, in the sense that the corrected logical lifetime is below the lifetime of the raw coherence time of their individual cavities. So in fact, it's if you can build quantum error correcting code that uses as fewer modes or as little hardware as possible, it makes it much easier to use error correction to improve the logical lifetime. So this was the first error correction experiment that reaches the quantum memory lifetime break-even. This was from Yale in 2006, where they used this 4-component cat code I'm going to tell you in a little bit, that allowed the creation of a encoded qubit that has a lifetime of 320 that is above the intrinsic cavity memory lifetime of 290. It's also above the Ancilla superconducting Josephson circuit that is used in the system. So this was the first demonstration of being able to deliver an encoded qubit that is better, that is longer lived than any of the physical constituents that is used to build the system. And more recently, the Yale group used the GKP code or the grid state encoding and achieved more than twice of break-even performance for quantum memory. So a question that you may ask is, can you engineer some dissipatively stabilize the quantum system to store quantum information longer than the intrinsic coherence of its constituents? Can we convert these kind of hardware efficient single mode quantum error correction idea and combine that with dissipation engineering, so that we have a passively corrected quantum memory that is better than the bare cavity itself? And this is the experiment I'm going to mainly tell you about. In this experiment in our lab, we used this so-called 4-component cat code, which is, by the way, is the same code as the early Yale demonstration. So the code works in the following. We're going to use a cat state, which is a superposition of the positive coherent state and the negative coherent state. So these are sort of the pendulum states swinging to the opposite side in position space. With a minus sign superposition, which give you a negative Wigner function value as shown by the blue fringe in the middle. So this state, this cat state, we're going to call it the plus x state on the logical block sphere. And the minus x state, which is orthogonal to plus x, is going to be the vertical cat state, which is 90° out of phase versus this cat, or plus I alpha versus the minus I alpha state. This is the minus x state. And using these two orthogonal states, we can create fill out the entire block sphere. So the block sphere will look like this. The North Pole state will be 159 superposition. The South Pole state will be 3711 superposition. You can take your math and to add the plus x and minus x, and you're going to see that all the photon numbers are 1 mod 4, and this is going to be 3 mod 4. So the nice property of this code, and this is the reason we construct code like this, is that this entire code, this entire block sphere is made out of states that contains odd parity of photon numbers. So the entire block sphere would have photon numbers of 1, 3, 5, 7, so on and so forth. So the reason the code is constructed in this way is that the natural photon loss, which is the dominant error in such a harmonic oscillator, in our case superconducting cavity, is that a photon loss will bring you from the odd parity code space to the even parity subspace. A 159 superposition will become 048, and the coefficients are completely computable from the bosonic factor. So a block sphere will remain a block sphere, except that you map from odd to even without killing the quantum information in the process. So if you can keep track of the parity by, for example, measuring the Wigner function fringe there in the middle, if you have a way to keep track of the photon number parity, you will be able to keep track of which block sphere you're in, and therefore allow you to perform error correction in the system against single photon loss. So this was the principle of the 2016 Yale experiments, where they did repetitive active QND measurement of the photon number parity. So this is the usual paradigm of measuring the error syndrome, do classical processing, and perform a feedback onto your quantum system in order to correct the errors. So what we want to ask the question is, can we engineer some dissipation, which is going to map this even parity block sphere back to the odd parity block sphere by essentially making the environment to prefer one of the block sphere over the other? So the strategy we're going to pursue is a discrete version, where we first do a truncation of photon numbers because you really don't need, you can use a relatively small photon number for the cat code. Even the Yale experiment used very small cats. So the larger the photon number above 8 or 9 have very small probability in this kind of code anyway. So we're going to truncate off, and we're going to try to engineer dissipation, which make 0, 2, 4, 6 to be unstable and 1, 3, 5, 7 to be stable. So if you can engineer such dissipation process, once a photon loss error happens that goes down the photon ladder, you can just pump it back up. And you want to do this coherently in order to correct the error. So the whole process is that we're trying to engineer a dissipation, which we call parity recovery, by selective photon addition. We select on these even number of photons to add a photon back to the system. So how do we engineer dissipation? In general, you're looking at some kind of optical pumping process, right? So this is a diagram that if you can add a photon while exciting some kind of a dissipative ancilla, which doesn't like to live in these metastable states, then you can go through some kind of optical pumping path to add a photon to the system. And this we know can be done in superconducting circuits with 3 or 4-way mixing process. But the issue is that you must avoid destabilizing the code space. You want to really make sure that the 0, 2, 4, 6 are the unhappy states, but the 1, 3, 5, 7 are happy states, right? So in order to stop this kind of process that you don't want, you can think about using some kind of frequency selectivity. So if we have the usual dispersive Hamiltonian in circuit QED, as I'm going to show you, you can make these transitions to have different frequencies as well as this transition. So you drive only specific frequencies and you avoid driving this kind of frequencies. This is how we can get the selectivity of these transitions. But you may notice that these dissipations now, these emission processes now would have different frequencies. This means that the environment, which is kind of some analyzer, is going to figure out which dissipative path that you have gone through. And this will be sort of an eavesdropping process that dephases your logical information. So in order to combat this process, we realized that we can use a two-stage pumping process to sort of to erase this information. The process goes as the following. We're going to have a superconducting cavity. This stores information, and the photon number is going to be represented by the first digit of the wave function. And this storage cavity is going to be coupled with a superconducting transmon ancilla. This is a two-level system that is really used as an ancilla for this error correction process, which is also dispersively coupled to a linear oscillator, which is the reservoir mode. So this is the Hamiltonian. This is the key dispersive shift term between the storage and the two-level system. So if a photon loss happens in the storage, let's say if it starts in 1, you lose a photon, it becomes 0, and the second digit represents the transmon is in ground state, and the third digit represents the lossy reservoir mode, which is also a harmonic oscillator, is in ground state. Now imagine you have a constantly on CW drive, which connects the transmon ground to excited state. The frequency exactly matches this transition, which is conditioned on the photon number being in 0 in the storage mode. This is basically your usual CW Rabi drive on your transmon, but it only works if you have no photon in the storage mode. And the 1G to 1E is not driven because of dispersive shift. There is a chi frequency difference for this transition versus this transition. So if the drive is not too strong, then you only do this drive. And you connect that with the second stage of drive, which is a four-way mixing drive on the system that excites the transmon from 0 to 1. It adds a photon to the storage from 0 to 1, while de-exciting the transmon from E to G and adding a photon in the reservoir mode, in the lossy resonator. So this is a process that is well known in superconducting circuits. For transmon, it sort of acts as a four-way mixer. Once you're in this state, because it's metastable, right? This state is going to decay to 1G0 because the photon in the reservoir mode is short-lived. So this tells you that if you have these two CW drives on, then the 0 is going to be automatically moving to one state. So we can do this process 4 times. We're going to use a comb of 4 drives with a frequency spacing of 2 chi to target the 0, 2, 4, 6 states. And we're going to use a comb of 4 drives to target these four-way mixing transitions. And you see that all these drives, they have incrementally like a lower frequency going up, and these drives have incrementally higher frequency going up. The net result is that these dissipative processes, they have the same energy or same frequency. And therefore, if you activate this transition versus activate this transition, the environment wouldn't know which transition has happened. So the environment would only know some correction, autonomous correction process has happened, but it doesn't know whether you're coming from this path or coming from this path. And this is the key to preserve the quantum superposition in this engineered dissipative process. So this will be the effective dissipation operator. Yes, questions? Okay, so the question is, even these dissipation have the same frequency, same emission frequency, but can the environment distinguish from the temporal profile or the rates of these dissipation? The answer is yes. If the rates are different, then the environment would be able to infer which path is coming from, depending on whether the emission happened early in time or later in time. Therefore, it's also important to engineer the temporal profile to make sure the rates are the same. So that's actually what we did in the experiment. So this effective dissipation operator, when you adiabatically eliminate the intermediate states, it only works if the rates are also the same for these paths. So this is the experimental hardware we used in our first generation of experiments led by my grad student, Jeff Girdler. This was published a few years ago. And you can see that this is our superconducting cavity. And there is a chip in the middle, which contains a transmon ancilla that is the aluminum on sapphire standard superconducting qubit fab. And there's also an on-chip strip-line resonator, which is strongly coupled to a coax cable, which is our readout or reservoir mode for the system. So the key parameters are that we have dispersive shift of 1.3 megahertz, which is the speed limit of how strongly we can drive the system and do the correction. And the T2 time of the storage mode is about 380 microseconds. And one bane of the experiment is that the transmon is slightly hot with 5% of excited state population. This thermal transition is going to be a major source of the error for the experiment. So I'm not going to go into detail of the experiment. So that's a very standard superconducting circuit QED setup. This is our device. It's in the dilution refrigerator, and we have a room temperature AWG where all four the comb is simply just done numerically with the 4 different IF frequencies programmed in the AWG on the same carrier tone. And therefore, you really don't need that many generators. You just numerically compute the 4 different modulation frequencies and add them together to drive the system. And we don't have single shot readouts. And it's amazing that we're talking about quantum error correction without being able to do good readouts. So we just drive on the system. So here's how the experiment works. The first experiment we do is we start in vacuum and we turn on a bunch of pump tones as we have described. And then we do this transmon spectroscopy, which is a method to analyze the photon number distribution in the system, because the cavity frequency, the exact frequency of the transmon tells us whether we have 0 or 1 or 2 or 3 photons because of the frequency shift. So you can see that at t equal to 0 initially, the transmon frequency is right here, which is the 0, the original frequency. But over time, it jumps to a frequency that's 1 chi shift to the left, which tells us the system has jumped from 0 photon to 1 photon dissipatively without oscillation. So this shows you that we have a dissipative addition of photons from 0 to 1 state. And you can see that initially the transmon is the cavity is at 0, and after 25 microseconds, the cavity jumps to 1 photon Fock state. This is a dissipative process, and you can see there's no oscillatory behavior. So we also can perform different cavity state preparation using some numerical pulses. This is some numerical computed pulses that we can use to prepare this even photon number parity cat state. And if we prepare 0, 2, 4, 6 superposition state and we pump on the system over time, you can see that it gets converted to a 1, 3, 5, 7 state. So this tells us this process allows us to add photon, and it only adds photon if the cavity contains even photon numbers. And this is the temporal, the time domain measurements where we pump for variable amount of time. In other words, a cut vertically here. We can show that from 0 to 1 conversion, the characteristic time scale is about 8 microseconds here. And if we prepare 2 states, it converts to 3. If we prepare 4 states, it converts to 5. And if we prepare 6 states, it converts to 7. And to loop back to your question, because all these modulations on the different fingers of the comb can be controlled by the AWG programming. So we tweak the amplitude of all these different IF modulations to control the magnitude of the drive for the first leg of the pumping and second leg of the pumping in order to line up the temporal profile of these conversions. So you can see that they all have the same characteristic time scale of the conversion, and that's a way to make sure that the environment wouldn't know which path the dissipative process has gone through. And from that, we also can extract the parameters of these drive strands. So, of course, those experiments don't tell you about the preservation of quantum coherence between the different photon number states. So here is a demonstration. We can prepare the pairwise superpositions of these even photon number superposition states, and we pump on the system for 25 microseconds with the comb pumping. And you can see that these even superpositions become odd superpositions. And these are the Wigner functions. And we did density matrix reconstruction. And to convince ourselves that these are the final states. Well, these are the states that it converges after a certain amount of time. And the off-diagonal elements of the density matrix tells us how much preservation of coherence we have. It's roughly 2 out of the 3 times the pumping is able to add a photon to the system while preserving the quantum superposition between these photon number states. So it's not great, but still, if you're able to correct 2 out of 3 errors, that's still an effective error correction. So now we can test the error correction performance by preparing the 6 cardinal states of the logical block sphere. So these are 0, 1 logical, as well as the 4 equator states. So these are the original wave function that we can prepare in the cavity. And if we just leave these cat states sitting in the cavity without doing any kind of active measurement or any kind of engineered dissipation on the system, so this is what we call the free cat evolution. After 144 microseconds of intermediate time, we can remeasure the Wigner function, and you can see that all the interference effects and the cat state phase information would be relatively scrambled. And for the same amount of time, if we also don't do any kind of a fancy active measurements, we just turn on these engineered dissipation in the system, you can see that the information is returned by a much greater extent. In particular, you see that the center pixel of the Wigner function is still blue, which tells you, if you're familiar with the Wigner representation, this tells you the photon number parity remains to be odd to a very good extent, which is by nature of our even to odd engineered dissipation process. And you can also see that the phase information, like a north pole, a south-north, a vertical cat will be still vertical after we adjust for some rotating frames in the system. The phase information is still retained to a great extent, which indicates that the logical information is preserved in the system, at least compared to the free cat. Now, to be more quantitative, we can also decode the cat state back to the transmon ancilla and do a tomography on the transmon ancilla so that we can quantitatively analyze what is the fidelity of the qubit after a variable amount of time. So if we just encode and then we do a free cat evolution and decode, you can see that the information lifetime is about 130 microseconds without error correction. And with the error correction, we're able to improve the information storage time by about 2-fold by pumping on the system. So this is proof that the error correction is helping with retaining information in this cat code. But quantum error correction is always associated with an overhead. So by using a cat code, which is a multi-photon state to encode information, as opposed to simply just put your quantum information in the superposition coefficient between 0 and 1, which is the raw cavity, the simplest information storage you can put in your cavity, you're paying an overhead of a 3.4 times by using an error correctable encoding. And this error correction is not able to overcome the overhead, and therefore this is below this break-even point for this generation of experiment. So the dominant error in the process, one is that the correction is not fast enough. So there's a second order process, there's consecutive photon loss. It also has a bunch of some spurious effects. One is ancilla decay, which is an uncorrectable error, as well as we have some spontaneous excitation of which is coming from the thermal process on the transmon, which is a very damaging process in this experiment. So in order to improve in terms of the autonomous error correction experiment, over the past couple of years, we've looked at more carefully, analyzed the protocol, and we moved to a second generation of an engineered dissipation process. This time, we use the second excited state of the transmon. So instead of pumping 0G0 to 0E0, we transit through the second excited state of the transmon. So this is a bit more technical, so I'm not going to go into the details. But the benefit is that we can produce a fast correction with less code space destabilization with this process. It also has less impact from ancilla heating. The primary reason here is that using the second excited state, we have twice the dispersive shift from the ancilla. Therefore, we are allowed to drive the first stage slightly stronger with a better frequency selectivity. So also, the second stage forward mixing now involves the two transmon excitations, and this is a stronger forward mixing processes. It's a more effective use of the nonlinearity of the transmon ancilla. So this is an experiment that my grad student Shudi has led, and yeah, we're in the paper is not out yet. We're still writing it up. So these are some detailed parameters, and I only just want to note that a few things. One is that we lower the transmon frequency to 3 gigahertz. This is because we're exploring a really high frequency of forward mixing process, which is not quite typical in circuit QED experiments. And it turns out high frequency pumping works. And we have a colder transmon, which helps with this spurious process in the system to add photons to pump more energy into the system. And we have a better frequency selectivity by combining the GE chi and the EF chi, therefore to get this faster correction. But unfortunately, over a period of 1 or 2 years, we had a fairly bad cavity lifetime in the lab. So this is done on a much worse cavity. If the cavity lifetime is better, we would have a better experimental outcome for this experiment. So here's to show you that we're able to perform these photon addition processes in the time domain with a faster process, about twice the speed of the correction, with much weaker drives on the system. So people in superconducting circuits would know that if you put a strong off-resonant pump on the system, you tend to excite some unwanted transitions, and you tend to heat up the system. So in the previous generation of experiment, we're stark shifting the transmon by more than 1 megahertz for a single pump, and overall it's about 3 megahertz of stark shift. Stark shift is a good measure of like how strongly you're pumping, how much you're pumping the nonlinearity of the system. We're able to use much weaker pump tones on the system while correcting much faster in the new experiment. And also in the old experiment, if we pump on the system for infinite amount of time, the steady state, you can see that it's a pretty nice like odd parity state. You can pump on the system for infinite amount of time, and the system still kind of behaves with the parity mapping. But you would expect that you should get a 1 photon Fock state at infinite time, because there's no mechanism that should drive 1 to 3 states. But that is a spurious effect coming from the transmon thermal excitation. And we can see that the new experiment is much better in terms of suppressing this the spurious channel of error for the logical qubit. So ultimately, even with the relatively bad cavity lifetime, we're able to achieve about a 200 microsecond of a corrected cat state encoding compared to the FOC01 encoding of 190 microsecond. So we're roughly at the break-even point here. Over time, we tracked this over about 10, 15 days. And on average, we have about a 5% improvement of the dissipatively pumped system compared to a raw cavity. So this is the first autonomous error correction experiment at the break-even point. I should note that more recently, I've seen a couple trapped ion experiments, which are also dissipatively stabilized with multiple spin states that are autonomous in some ways that are above break-even. So the takeaway from this experiment is that we're able to convert some really complicated FPGA programming that my former colleague, Nissim Ofek at Yale, had to work many years to do firmware encoding. And eventually, this technology has transformed into this company that he co-founded that is worth a lot of money. This is the active quantum error correction. It's very hard, very difficult to do, even though it's becoming much easier today with all the technology improvement. We're able to simply replace it with this complex logic with some dissipative process in the system that you do need to calibrate them, but you don't need single shot readout or FPGA feedback to do it. So you just keep pumping, and this cat can actually be healthier than before. Yeah, it's an unusual cat, right? So yeah, so the idea of dissipation engineering, of course, has really taken root and in many areas of quantum information science. And there are also different varieties of autonomous error correction. People do continuous drives on more transmon-based system, and you can also run some autonomous duty cycle error corrections without any information exchange between your classical controller and the system. But you can do things not fully continuously, but in duty cycles, which has been done in other types of superconducting cavity-based experiments, as well as in trapped ion systems. This is using motional states for bosonic error correction. So in the remainder, maybe I'll take 10 minutes to talk a little bit about our ongoing experiments towards multi-mode error correction. So once we have a bosonic encoding on a single cavity, one natural way people are already working on, as you've seen from the Amazon experiment, is to concatenate with a regular bit register-based codes. But an alternative strategy is to, I may argue, is the more intrinsic strategy to fully use the Hilbert space of many bosonic modes, is to use multi-mode entangled states to encode logical qubit. And the benefit is that you can actually correct, you can be more fault tolerant, and you can correct more errors. So currently, all the experiments have done with one logical qubit is one bosonic mode plus a transmon. And the issue, as I will show you, is that it's when people discuss these bosonic error correcting code in theory land, you think about your oscillator as your media, and the ancilla is something else. And it's often you're often correcting errors in the bosonic oscillators, but the errors in your ancillary circuit is oftentimes uncorrectable, which is certainly true for the experiment I showed you earlier. And there are new directions using multi-mode that can be robust against all first-order errors in both the storage cavity as well as your ancillary qubit. So in this particular case, I'm going to tell you about this pair cat code that allow us to close one of the dominant sort of error channels in a previous experiment. So this is a different representation of the same experiment I've showed you earlier. You have your logical space, that's 1, 3, 5, 7. This is your error space, 0, 2, 4, 6. So in the rotating frame, this space is degenerate, and this dissipative space is also degenerate. That is why the error correcting code works. But the issue is that the intermediate state, where in between the two pumping combs, this intermediate state is an entangled state between the storage cavity of the 0, 2, 4, 6 photons with the ancilla excited state. And because of the dispersive shift, these states are not degenerate in the pumped frame. And therefore, if you have an ancilla decay, an ancilla T1 process decay from E to G, that is going to dephase your logical information because you don't preserve the frequency degeneracy in the entirety of the pumping process. So this is a vulnerability that is intrinsic to all these single mode bosonic QEC codes. Whether it's a CAT code or the GKP code, you do it actively or passively. This is a problem that you're not getting away with. So there is an alternative strategy, which is actually developed by Victor Albert. I don't know if he's here. Victor with Liang Jiang during his Yale time developed this code called the PairCAT code. So you have instead of using 1357, you can use 11223344, which is the photon numbers in two storage cavity modes. So now instead of using a parity subspace, you use the subspace with equal photon numbers or photon number difference of 0 to encode your code. And now if you have a circuit Hamiltonian that has these two storage modes with equal and opposite chi, this will allow you to have all these states to be degenerate. And after photon loss, you have photon number difference instead of 0 to be 1. They're all degenerate. But also your ancillary space, when you pump on the ancilla qubit, you also have this degenerate intermediate states, because all these states have photon number difference that is equal to +1. And if you have this negative chi matching condition, you will be able to engineer the situation that your entire dissipative error correcting process to be degenerating in frequency. So this is a strategy we're going after currently in the lab. So your logical qubit in this experiment will be never entangling with your ancilla, and therefore your transmon is free to jump from G to E, E to G, G to E, E to G, and it's not going to have an impact on your logical information. So in this protocol, ancilla relaxation will cause no harm to your logical qubit, and therefore this is said to be fault tolerant against the ancilla decay in the process. So the code word for this code is the pair coherent state, or the pair CAT state. So the math goes as this: coherent state is a Poisson distribution, is a Poisson superposition of Fock states. And the pair coherent state, by extension, is a Poisson distribution of the pair Fock state, where you have n plus delta photon in cavity A and n photon in cavity B. So the pair coherent state is described by two good quantum numbers: the complex amplitude gamma, just like alpha for coherent state, and there's also photon number difference delta that describes what is the photon number in A minus photon number in B. So this is the delta equal to 0 photon number distribution, which is the code state we want to work with. And it has some nice properties that the state is an eigenstate of pair photon subtraction operator, as well as the photon number difference operator. So in the first sort of learning experiment, we have engineered a dissipative process which stabilizes the PCS manifold. So this is a pair photon extraction dissipation operator, which is not enough eventually to do the PairCAT code, but we were able to stabilize and study the properties of these pair coherent states. So if we pump from the vacuum state, we're able to stabilize this state, which has have a positive Wigner fringe. And if we start with one photon Fock state in cavity A or B, the system will converge to a PCS state with delta equals 1 or -1, as demonstrated by the negative Wigner fringes in the middle. So this was an analysis experiment. We're able to prepare these PCS states for the first time to our knowledge, and we developed some protocol to analyze the coherence for these PCS states. And moving forward, of course, what we want is to use these states to build an error correcting encoding, where for example, we're going to use this pair cat code that is a superposition. The code state is a superposition of a plus alpha, plus gamma, and minus gamma state in the PCS representation. So you can think about this as your plus state is 002244 superposition, and the minus state is 1133 superposition. Just as I showed here, this will be your code space. So the real challenge for this experiment is actually to realize a Hamiltonian with the negative chi matching condition. So if you're familiar with a transmon system, you have a transmon, you have cavity, you have them dispersively coupled to each other. In general, you're working with the far detuned regime, where usually you have a transmon far detuned from the cavity. They have a James-Cummings interaction, and that gives you the dispersive shift, which is often negative for transmon system. So you can't have positive and negative chi and have them to match with each other easily. So there was actually an experiment in Michel Deveray's lab working on this with some pump game on transmons. It's very difficult to really fully reverse the chi for a transmon and the cavity system. So what we work with in our lab is using fluxonium ancilla, which is there are a couple experiments in the field now trying to integrate fluxonium qubits with superconducting cavity. I'm not going to give you an introduction of fluxonium now. Many of you probably have heard of this from a former colleague many times. So this is a fluxonium. I just want to say that it's an awesome qubit, has very long coherence times. Many of these works are done in the Maryland lab here, including this recent experiments with 2 fluxonium gates reaching 3 nines and a 4. I see grad student here that you can talk to him. So in our lab, we're trying to integrate this low frequency fluxonium qubits with 2 storage modes. And the great benefit here is that you can place the fluxonium has very large anharmonicity. So there's a very broad frequency range that you can put the cavity A and cavity B in the straddling regime of the fluxonium qubits. Namely, you have omega A below 1-2 transition and omega B above the 1-2 transition. This will give you a natural negative chi matching condition. So this is some very preliminary results in our lab, and we engineered this hardware system. So this round of fab didn't hit exactly the EJ parameter we want, but nonetheless, the natural system gave us this is number splitting experiment that tells us about chi A and chi B. You can see chi B is negative and the chi A is positive, so it's already somewhat close to the negative chi matching condition. So we're able to use some pump drive on the system. This follows an off-resonant drive strategy that was demonstrated a few years ago to fine-tune the dispersive shift in the system and reach the condition where the negative chi matching is met in the system. So this particular device has some other problems, especially the cavity lifetime is very short due to the hybridization with one of the dissipative mode in the system because of the frequency misplacement. But we think we're on the right track to do some 2-mode error correcting experiment using this negative chi matching condition. So just to summarize, hopefully I've convinced you that autonomous error correction is a very interesting science game, and it can also be a resource efficient strategy to counter the dominant physical errors in the physical hardware for qubits. And I've primarily talked about the single mode single photon loss correction using the CAT code. The CAT code, by the way, is also very similar to the binomial code. To me, they are rotational symmetric family of codes, very much of the same origin. And a new direction we're working on is the the pair cat encoding and autonomous error correction with the fluxonium ancilla. So with that, I'd like to acknowledge that my funding agencies and my grad students, especially Sean, Shuli, and Ying are the current graduate students working on the fluxonium and pair cat project. And finally, as Alicia has already said, I will be moving to University of Toronto and building my new lab there. So the transition is sort of underway with the lab preparation. So if you are going to be a grad student or a postdoc and interested in various opportunities, please let me know. And if you know anyone who's really looking into moving to Canada, this will be also a good opportunity. Okay. Representation of the pair coherent states. What do you need a phase parameter between the two. Let me. Yeah, okay, so the question is whether there should be a phase in representing the pair coherent state. So here, so let's think about let's talk about coherent state here. There is this alpha is a complex number. Which tells you what is the cascading phases between 0 and 1 and 2 and 3 for a coherent state. This is single cavity coherent state. So similarly for pair coherent state, gamma here is a complex number that runs into the phase between 0, 0 and 1, 1, and between 1, 1 and 2, 2, and between 2, 2 and 3, 3. So so that is the only phase that we have for a pair coherent state. So it is we do not it is there is no phase to speak of between cavity A and the cavity B for a pair coherent state, because when you think about when you define phase for A and the phase for B, then you're sort of defining a superposition within A and a superposition within B, and then you entangle the two states together. So in this particular case, actually the phase of gamma is imprinted in between pair photon numbers. So you cannot distribute that into phase in A or phase in B. In fact, it's indistinguishable in terms of which phase you put it on cavity A or put on cavity A or cavity B. So in some sense, this is a very interesting quantum optical state that it's intrinsically multidimensional entangled. So if you check like how many E-bits of entanglement, this is more than a bell pair between the two cavities. And for this kind of a Wigner function representation, so for these states, for this superposition coefficients, if you're trying to do a Wigner function, a joint Wigner function analysis, you can show that if you add a phase on cavity A to do the phase space representation, or put a phase on cavity B to do the phase space analysis, the state you see is exactly the same. So it only cares about the common phase in A and B you put on it to do a displacement operator and the Wigner analysis, and it doesn't care. It only cares about the common phase, but not the differential phase between the two cavities when you analyze the quantum state. Yeah, do you call an audience or should I just say? Okay, yeah. Okay. So for profile, the short time scale is different photon numbers are indistinguishable. Long time scale is very saturated with different populations. Oh, okay. How does the autonomous qubits protocol affect your data operation? Okay. Okay, so first question is about the fact that the environment can distinguish which path you're going through because the conversion efficiencies are different. So first of all, the conversion efficiencies are different, are worse at higher photon numbers, simply because we have finite correction speed, which is in constant battle faster decaying from 7 to 6 than from 1 to 0. So that's why the higher photon numbers, the corrections are harder. The basically the fidelity is lower. So that already is a fundamental problem. It is a problem, but of course it's a second order error because you're basically talking about you lose a photon, then you correct, and then another photon loss has happened. So it's a second order process. So if you do have a second photon loss happen in the system, then you're already dead just by error correction standard. So if you are already having a full bit flip going from 1 mod 4 to 3 mod 4 states, then no matter what the logical qubit is no longer preserved. So you wouldn't worry about the phase information at all, right? It's just like if you already have a T1 error, then you don't have to worry about T2. So in some sense, this is just a question of can we correct faster on the better to begin with. So that is the answer to that. And the second question is related to logical operation in the presence of autonomous error correction. So I want to first say that we are working with with single cavity code that is relatively difficult to do logical operations. So there have been works done on CAD code, single cavity, 4-component CAD code, performing X gate and performing Z gate. So the Z gates are a little bit easier. It doesn't involve adding or subtracting photon numbers. So the X gate will require adding pairs of photons and extracting pairs of photons in this code. So so the gates by themselves are not that easy to do. You can do it on maybe close to about 2 nines of fidelity, but it's not as good as transmon yet. So there are also works done with error correction with active error correction combined with these gate operations. So this kind of pumping gains that you're converting odd even photon number manifold into odd photon manifold, it would be compatible with both types of gates. So you can think about doing gates in the presence of these drives on the background. So that is possible. The challenge though is that the dominant error for these kind of CAD code gates is coming from the ancilla decay, because for error correction, we do use the excited state of the ancilla. We transit through the excited state of the ancilla in order to do this correction. But you can keep it at a minimal. You can, because you see that this drive, this pumping path doesn't get activated until until a photon loss has happened. Then it activates the AQEC process. So if the natural photon loss is infrequent, then your ancilla is also not too frequently excited. But when you try to do gates on this encoding, you basically actively are trying to excite your ancilla to draw the resource there in order to do this gate. And therefore, basically the 99% fidelity, if you want to do gates on the CAD qubit, is going to be primarily limited by T1 error of the ancilla, which this code doesn't correct for. So I guess it's a little bit of a long answer, but to summarize, this pumping, this AQEC does not stop you from doing gates, but it doesn't quite give you a big benefit in terms of improving gate fidelity yet, because it doesn't correct the ancilla error, which happens during a gate. Yeah.
People are hungry.